Neptune, the outermost planet. We've arrived at the big blue one. Okay, and some vital stats. Semi-major axis, 30.1 AU. So the gap between Saturn and Uranus is approximately the same as the gap between Uranus and Neptune. We're now about 3 billion miles out from the sun, way out there. Not much sunlight out there. The orbital period for Neptune, 164 years. Nobody has lived long enough to see Neptune orbit the sun once. In fact, most people barely make it, if they do, to see it orbit 1/2 of the way around. 164 Earth years for one trip around. The rotational period, pretty much on par with the other outer planets, 0.67 Earth days, which is about 18 hours or so. The mass is 17 Earth masses, a little bit heavier than Uranus, but the radius is a little bit smaller, so it's a little more dense. Really, in a lot of ways, I should say this right now, Neptune and Uranus have a lot in common. Now, Neptune doesn't have the weird seasons. That's one of the reasons I talk so much about that for Uranus, because that's unique to Uranus. Doesn't have the weird seasons and the big axial tilt, as we'll see in just a second. But really, for a lot of reasons, Neptune and Uranus are similar. Their compositions are similar, their sizes are similar, their magnetic fields are similar. The composition, so a lot that's similar. Number of moons, we're now down to a mere 14 moons. There certainly are more, but Neptune's hard to see. To find moons of Neptune is a trick, but there may be a couple more, but we think we've gotten most of them here with 14. The density of Neptune, again, very similar to that of Uranus, but a little bit, the density has to be a little more because Neptune is slightly smaller than Uranus, okay, but has more mass than Uranus does. So it has to be have a higher density. That's what that means. So the density is a little bit higher, very similar to the other gas giants, except for Saturn, 1,600 kilograms per meter cubed. The obliquity it has seasons, 28.3 degrees, okay, but it's not like Uranus, tilted 98 degrees. Magnetic field is similar to that of Earth. Again, down inside of Neptune, the field is much larger, but on the outermost layers of the atmosphere, the part that we see, the field is about the same as that of the Earth. Eccentricity is very low, almost as low as Venus's, but after Venus, Neptune has the most circular of orbits among the planets. And finally, its surface temperature is 72 kelvins, which is minus 330 degrees Fahrenheit. Now, this might seem really cold. It should be colder. Neptune has a significant heat source within it, and the textbook talks a little bit about that. This is a little warmer than we would expect Neptune to be. Remember, Uranus was 76, which is only 4 kelvins higher. We expect if you add another, billion miles away from the sun that the temperature would go down more than 4 kelvins, but it doesn't. That's because Neptune has its own heat source, maybe radioactivity from inside of it. I can't remember what the details, what they say in the textbook. There's actually some debate about that. But anyway, those are the vital stats for our friend Neptune. And I do want to also put the composition of Neptune up here quickly to compare it with Uranus and the other gas giants. So the composition, hydrogen is 83%, not 84, I think is in the case with Uranus. Helium is still about 14%, but now methane, CH4, is up to 3%. So the increase in methane. This methane, remember, is what causes the nice blue color. So this 1% increase in methane Remember, Uranus had 2% methane. Neptune has 3%. That's enough to turn the color of Neptune from sort of a sea foam kind of greenish blue to a deep, intense blue color. So that's where the blue color comes from. Neptune is a beautiful planet. If you like blue, you'll be loving yourself some Neptune. That's the truth. Okay. Now, what I want to do here, talk about Neptune, is not really any of these numbers necessarily, but talk about how it was discovered, because this is a great story. I can't do it full justice here, but here's the basic idea. Neptune, let's go back to Uranus. Okay, Uranus was discovered in 1781. So 1781. Yes, I know I'm talking about Neptune, but we got to start our story of the discovery of Neptune. This is about the discovery of Neptune. The discovery of Neptune starts with the discovery of Uranus, which, by the way, the discovery of Uranus was the first discovery of a planet in recorded history, right? Because Saturn had been known about since, long before history started being written down. Saturn was known about. Uranus was not. So Uranus was discovered in 1781, and it was a radical big deal. Now, I'll draw a picture here for you. At the time that Uranus was discovered, 1781, Newton's theory of gravity, I'm going to erase this so I can see you. Newton's theory of gravity had triumphed about 100 years before Uranus was discovered. So Newton's theory of gravity was enormously successful. It predicted all kinds of things. It solved problems that weren't even problems yet. Oh, by the way, we're in sections 13, 1 to 3 here. So the Newton's theory had triumphed. Everybody believed it was true. And so what Newton's theory did was predict a certain motion for Uranus. Right, so let's say here's some background stars. Let's say here's the ecliptic. There's the ecliptic, not the eclipse, the ecliptic. Well, here's the deal. Uranus was discovered. Okay, so let's say that this is the location of Uranus when it was discovered in 1781. About 50 years later, Uranus was, say, here. Over 50 years, maybe 60, but between 40 and 60 years. So a long time later, Uranus went from this point to that point in the sky. I don't even know what constellation it was in. Let's say it was in Taurus. So these are the stars of Taurus. And so there's an ecliptic going through Taurus, and Uranus travels west to east along that ecliptic. Now, that's all fine and good, but the trouble is that Newton's theory had triumphed, and Newton's theory said that Uranus should be right here. That is the predicted location. Uranus. In other words, where Uranus showed up right here after 50 years of motion, after being discovered, it showed up there, but the math said it should have showed up where the pink circle is. That's where you expected to find it. And so by about 50 years, it turned out that Uranus was 1/4 of an arc minute from where Newton said it should be. Now that's not very much. 1/4 of an arc minute That's about 1/120th of the width of the full moon. How about that squeaky sound? So Uranus was not where people thought it should be. It was 1/120th the distance of the width of the full moon, different from where it should be. So this distance here, basically, let me make it in blue. This distance here between where Uranus showed up and where it should be was 1/4 of it. That's not 11/4. That's 1/4. That's a prime symbol, which is the symbol for arc minute. 1/4 of an arc minute. And that was enough to convince astronomers at the time that something was wrong. So by the time we're approaching sort of the early mid-19th century, something was wrong with the position of Uranus. And so what they decided was that that could be explained if an eighth planet existed. In other words, maybe the gravity of an unseen planet produced that difference between where we thought Uranus would be and where it actually showed up. Okay? So maybe there was an unseen planet tugging on it. And that's what caused the difference. And it turns out that a couple of mathematicians, Adams from Britain, from and Leverrier, I think I spelled that wrong. I think there's an A in there somewhere. No, that's right. Leverrier. I got my L's to be R's. Leverrier from France. Both predicted the existence of Neptune. And in 1846, right, 1846. A German by the name of Gall found Neptune on the first try, within 1 degree of the position that Adams and Leverrier predicted. In other words, Neptune was discovered theoretically by math before it was discovered with a telescope. It's the only planet to be discovered that way. And this was a huge triumph, a major W for Newton's theory of gravity. That's a small difference. 1/120th the width of the full moon. That's that gap between where Uranus should be and where it actually was. And that, they predicted, was because of an unseen, never before seen planet tugging at Uranus, making up for that difference. Making that difference. And so Adams and Leverrier predicted where Neptune should be. Shortly after that, it was discovered by the observer in Germany. And so Neptune was discovered on paper, theoretically, mathematically, before it was seen with a telescope. That's not quite totally true, because it turns out, and I can't stand on my toes here to see you, turns out that Galileo had actually seen Neptune and recorded it as a star, but he never realized it was a planet. So, and that was in the early 1600s. So this is 150 years before Uranus was discovered. Neptune was seen by Galileo and recorded, but never followed up on. So Neptune had been seen before, but nobody knew that it was a planet. Kind of like Uranus had been seen and thought it was a star. But Neptune was seen long before Uranus was, which is kind of crazy, but true. And it was Galileo, but he never knew he was looking at planet number 8. See ya.